So yesterday, we talked about with rational functions how we have vertical asymptotes and or holes with any places that we have domain or values that we exclude from our domain, right? Which are the values that make us divide by zero. The last thing that I was hoping to get through yesterday, that we're going to talk about now, are horizontal asymptotes, which are a little bit different than the vertical asymptotes, mainly in the sense that they are not values that we exclude from our domain. Okay, it's a completely different concept. So a horizontal asymptote, first to just locate them, we're going to look at the degree of the numerator represented by the variable n and denominator represented by the variable d. And if you remember back from what we did before break, the degree is the largest exponent of a polynomial. So we're literally looking at the largest exponent for our numerator and the largest exponent for our denominator. And we're just comparing those. And so based on the size of those degrees, we're going to come up with three rules. When the numerator, or the degree of the numerator, is less than the degree of the denominator, then our horizontal asymptote is at y equals 0. And when we get to these examples, I'll explain to you how I remember these. Because to be honest, I don't have these rules completely memorized, okay? I think about it in a completely different way, which I will share with you all once we go through a few examples here. Right, then if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is at y equals whatever the ratio, and I should say ratio, not ration, ratio of the leading coefficients. Again, that's when the degrees are even for both the numerator and denominator. And then the last option is when the numerator is greater than the denominator, in which case there is no horizontal asymptote. Right, and then just some specific things about the horizontal asymptotes. First, know that there is only one horizontal asymptote, if any. Okay, so either one or none. There will never be more than one, unlike the vertical asymptotes, right? The vertical asymptotes, we could have, honestly, infinitely many. It just depends on the polynomial. But strictly one horizontal asymptote or no horizontal asymptote, that is an option. Now, what the horizontal asymptote is really doing is it's telling us what value the graph approaches as x goes to positive and negative infinity. Almost kind of like the end behavior of polynomials. So if we take the graph all the way to the left to negative infinity, what y value will the graph approach, if any? It's possible that it still goes up to positive infinity or negative infinity, but a lot of times it's going to approach a specific value. And since it's not necessarily a domain restriction, we can actually touch or even cross these horizontal asymptotes. The only time we can't touch them or cross them is when they cause errors in our domain, which that's not the case here. Right, and then we're going to go through an example of each, just identifying the horizontal asymptotes. So I'll give you a sec to write those down as well. All right, so like I said when I was going through these rules, I don't necessarily have those memorized, and you don't either. And this is also just kind of a good way to think about why these horizontal asymptotes exist in the first place. So when I look at a rational function, I'm noticing in example A here that the degree of the top is just 1 and the degree of the denominator is 2. So what I think about is what's going to grow quicker as we start to plug in larger and larger x values. When we square an x value, it's going to grow much quicker than just simply multiplying it by 4. And so because of this, the denominator is going to grow a lot quicker than the numerator is. And think about what happens as the numerator gets bigger, or excuse me, as the denominator gets bigger than the numerator. So let's just take an example of like 1 over 10 And if it grew even bigger to be 1 over 100, and then even bigger to be 1 over 1,000, well, what is this really approaching? It's approaching 0, right? That decimal, that fraction is getting smaller and smaller and smaller. So I know that in this case, my horizontal asymptote is going to be at y equals 0. Based on the rule, the numerator is less than the denominator, so that's another way to just confirm it. Okay, so our horizontal asymptote is at y equals 0. And again, it's because the denominator is going to grow much quicker than the numerator will as we plug in larger values for x. And so that's how I approach these. What happens when I plug in large values for x? So in part B, as I approach or plug in large values for x, they're both being squared. And so they're growing at essentially the same rate. And when they grow at the same rate, that's when we're going to pay attention to the ratio of the coefficients, or the leading coefficients. So this is the case where the degree of the numerator is equal to the denominator. And so our horizontal asymptote is that y equals 4 divided by 2, which is just simply 2. So this graph, as x goes to negative infinity and positive infinity, is going to approach 2. All right, in our last example, as I plug in large values of x, cubing those values is going to grow much quicker than squaring them. Okay, they're both growing fast, but cubing it's going to grow even faster. And so because of this, it's almost the reverse from what we saw in A, where our value is going to go from 10 to 100 to 1,000, okay, and just grow much quicker without bound. And since the numerator is growing quicker without bound, it's not approaching any value. And so in this case, there is no horizontal asymptote. And so this is the case where the numerator is greater than the denominator, at least to degree. And so there is no horizontal asymptote. Right, so however you want to go about memorizing those rules, it doesn't really matter. Find a way that works for you. Again, I like to think about it more conceptually. It eliminates me having to memorize all these specific rules there. I can just kind of figure it out as I go through. Okay, so we're going to pause there. The last thing, or last kind of new feature of these rational graphs is what's called a slant or oblique asymptote. So in total, there are 3 different types of asymptotes that these rational graphs can have. So the slant or oblique asymptote is a specific asymptote that only shows up if the degree of the numerator is 1 more than the degree of the denominator. Okay, so if the degree of the top is exactly 1 more than the degree of the bottom, that tells us there's going to be a slant or oblique asymptote. And so what we're going to focus on is finding the equation of that slant asymptote. And to find the equation, we're going to use polynomial long division or synthetic division. Okay, so there's more uses to that long division and synthetic division besides just simply factoring, right? Which is what we were using it for back before we went on the break. If you're jotting down the graph, this is that slant asymptote, and it will always be some kind of linear equation. That's what makes it slanted. That's also, when you think about doing this division, if the numerator is 1 more than the denominator, when we do that division, we're going to be left with a linear equation, okay, every single time. So I'll give you all a sec to jot these things down, and then we're going to do some division to find the slant asymptote. Okay, so we're going to go ahead and work through an example. We're going to find the equation of a slant asymptote. And I'm actually going to do it and then have you all do it as well. More so because we need that refresher on how to do the long division and synthetic division. So one thing that's nice is if you think about a rational equation or expression, it is division, right? This fraction really is division. One way we could read this equation is x squared minus 4x minus 5 divided by x minus 3. So that should give us some idea as to how to set up the division. Now we're going to actually start with long division here, even though synthetic division would work. So I'm going to take x minus 3, put it on the outside of our division bar, and we're dividing x squared minus 4x minus 5. So when we're doing long division, remember our goal is to be able to subtract away this first term, in this case the x squared. So I need to multiply x minus 3 by some term to get this x squared. In this case, it's going to be an x, right? X times x minus 3 is x squared minus 3x. And the whole reason that we chose x is so that these x squareds will subtract away. So x squared minus x squared is gone. And then I have negative 4x minus negative 3x, which is negative x. And that's a good example why the long division can be kind of annoying. Right? With all those negatives, it can be really easy to make a mistake there. Then I'm going to bring down the negative 5. And we start the process over. So now I'm thinking about what can I multiply x minus 3 by to get this negative x? Well, how about just a negative 1? Negative 1 times x is negative x. And negative 1 times negative 3 is positive 3. And then we'll subtract those terms away. Negative x plus x cancels out. Negative 5 minus 3 is negative 8. Now, with the slant asymptote, we will always get, is it positive 8? I'm making a mistake, Kate? Or do you have a question? Go ahead. But I'm minusing it. It's negative 5 minus 3. Yeah. With the slant asymptote, you will always get a remainder. Okay, and I was thinking about them like, why are we always getting a remainder? Well, think about when we did our long division, when the remainder is 0, what does that tell us about this term here? That it was a what? Anybody remember? It was a factor, right? And if it's a factor, that means it's going to be some other feature. Okay, more likely, it'll probably end up ending up being a whole or some other kind of feature for this graph. So we should expect to get a remainder when finding these slant asymptotes. So the equation of the slant asymptote is the quotient without the remainder itself. So this is our equation of the slant asymptote. Yep, remainder has no value in terms of what that equation ends up being. And now, like I said, we could actually have come up with this equation using synthetic division, which I still think synthetic division is much quicker, much more efficient. And the reason we can use synthetic division is because we're dividing by a linear term. Whenever we're dividing by a linear term, we can use synthetic division. But if we were, let's say this equation was x cubed up top and x squared in the denominator, then we absolutely would need to use long division, which is why I'm showing us and reminding us how to use both here. So for synthetic division, remember that we have this chair. Inside the chair is whatever makes what we're dividing by equals 0. So x minus 3, if I set that equal to 0, I get a positive 3, which is what's going to go in the chair. Then I'm going to bring down all the coefficients for what we're dividing, which is 1, negative 4, and negative 5. And with synthetic division, we are adding these terms, making it a little bit easier. So I can bring down the 1. That term does not change. And I do 1 times 3 is 3. Negative 4 plus 3 is negative 1. Negative 1 times 3 is negative 3. Negative 5 plus negative 3 is negative 8. This negative 8 is that same remainder that we got before. This negative 1 is your constant. And this 1 is your linear term, which is just an x. So this gives us x minus 1. We don't care about the remainder. So giving us the same equation. And we really should say y equals x minus 1, or f of x equals x minus 1. Not f of x, we have f of x, but letting it equal something. All right. I'm going to have you all just get a quick refresher on how to do long division and synthetic division with this example here. I don't care which one you do first, but please go ahead and try long division and synthetic division as a refresher. You have 2 minutes to do so. Okay, so in both cases, you should have found that the slant asymptote is at 2x minus 1. In both cases, you get a remainder of 5. And you can kind of check your work up there. I'm not going to go through each step. But yeah, hopefully brought back some memories on how to do both the long division and synthetic division. They do go away after this unit, but this is, yeah, we do need those refreshers. Before we close our stuff out, let me just kind of show you what's coming up. In that, when I see you all tomorrow, we're going to start to piece this together. And we're going to go through all these steps to graph a rational function. And there's a lot to it. Okay, think about just all the asymptotes we've talked about the past 2 days. In addition to that, we're going to check for symmetry. We're going to also find intercepts and some extra points to plot on the graph to give it a good representation. Okay, so there's a lot of steps that we need to follow to graph rational functions. What I have for us when I see you tomorrow is an actual packet, because graphing, it's always better to do it on paper as opposed to Math Excel. The last thing I will say is know that there is a Math Excel that is going to be assigned to you tomorrow, covering all this stuff. Okay, it's short. I think it's about 5 questions, mostly because 2 of them are going to take you some time. All right, that is it for today. We have about a minute left, so just hang tight. If you're going to be on your phones, you can. Once that bell rings, you are all set to get out of here.